Okay, 4-6, day 1. Your goal today is going to be to prove that a differentiable function is continuous. So, what does it mean for a function to be differentiable, first of all? So, differentiable just means that the function has a derivative. So if it has a derivative, it's considered a differentiable function. So in order to have a derivative, though, you have to remember that on a graph, the graph is smooth. No sharp change in directions, no breaks in the graph. Just got to be a nice smooth curve so we could draw a tangent line if we had to. Okay, got a continuous function. We had this three-part definition, I believe, back in the last chapter. A continuous function. To be continuous, three things had to happen. And it was at a specific point. First of all, f of c had to exist. The second thing, the limit as you approach c had to exist. And then the third thing was that these two values had to be the same. So the function value and the limit had to be the same thing in order to be continuous at a point. Well, today we're going to see a property that's going to shorten this little thing up for us. So we're going to look at what's differentiable, what's continuous in a graph. So differentiable and continuous. So our first graph here's another color, is going to have a cusp in it. So we're going to look right at that cusp spot. That's going to be our C. So, is this graph continuous here? Absolutely. I can draw that right through C without picking up my pencil. Is it differentiable at C? Could I draw a tangent line here? Well, no, all the tangent lines are positive here because I'm increasing. Then they switch to negative, and at that spot, they call that a cusp. No derivative there. So this is continuous only, not differentiable. Not differentiable here. This next graph let's pick a C value right about here. So that one is definitely continuous. I can draw right through that point. And it is differentiable. I could draw on my tangent line. It's a nice smooth curve. So this one is both differentiable and continuous. Well, there's a property in calculus. This property says differentiability, nice word, differentiability implies continuity. Differentiability implies continuity. What that's saying is if something is differentiable, then it has to be continuous. So as an if-then, if a function is differentiable, then it is continuous. So if it's differentiable, you could automatically say it's continuous. So for us, when they say prove something's continuous, we're going to find the derivative. If we can show it has a derivative, it's automatically continuous. So we're not going to have to go through this three-part continuity definition like we did in the last chapter. So here's where geometry comes into play. The contrapositive to this statement is also true. Contrapositive. Take yourself back a couple of years. Remember when we did inverse, converse, contrapositive? Remember the contrapositive, if you have an if-then, and that's true, when you do the contrapositive, which is switch them and take the opposite, that is also true. So the contrapositive to this would be if a function is not continuous, so remember, not continuous means there's a hole in it or there's an asymptote in it, some kind of a break, a step. So if a function is not continuous, then it is not differentiable. And all of these are at a specific x value. So if a function is not continuous at x equals c, then it is not differentiable at x equals c. So both of these statements are true. But remember, this is a one-way only. Differentiability implies continuity. If I flip that around, if it's continuous, is it differentiable? No. Take a look at this graph here. This is definitely continuous, but it's not differentiable. So this is a one-way if-then. If differentiable, then continuous. Or the contrapositive works. So using that property, prove that for f of x, which equals x squared minus 7x plus 13, prove that this function is continuous at x equals 4. And just plugging the number in here and getting a point doesn't imply continuity. That just means there's a point on the graph. Doesn't mean you can travel right through it. So what we're going to do is use that property I just said. If it's differentiable, then it's continuous. To be differentiable, it has to have a derivative. So if we just find the derivative at 4, and if that derivative exists, we've then proven that it's continuous. So our goal is to find f prime of 4. Show that it exists. I'll say show that f prime of 4 exists. So all we've got to do is do derivative. Nice easy derivative after the stuff we've been doing. 2x minus 7. That goes to 0. Now plug in the 4. If I get a real number, I'm good to go. Let's see, that's going to be 8, 1. So because the derivative does exist, nice real number 1, it's continuous. So I can say, therefore, that's old school, therefore, continuous. So, is g of x, which equals x minus 3 times 2x plus 4 divided by x minus 3, is it differentiable at 3? Okay, the long way to do this would be to do derivative, which has a product rule within a quotient rule. Plug the 3 in, see if we get a number. That'd be really long. the quick way is to use the contrapositive, that property that we talked about. If a function is not continuous, then it is not differentiable. Well, right away when I looked at this, and I see I'm looking at 3, and if I put 3 in here, I know that there's a break in this graph because that's coming out 0. And I know if I see the same factor in top and bottom, that's just a hole in the graph. So automatically I know there's a hole at 3, and then the rest of it would just be this line, y equals mx plus b, y equals 2x plus 4. And if you didn't know that, well, a couple things you can do. Graph it. Get that to not have so much glare. Say y equals x minus 3, oops, divided by, nope, times 2x plus 4, then divide by x minus 3. Yes, it comes out looking very linear, but again, you've got to know that when that denominator is 0, there's a hole in it. So, our proof of this is going to be the sketch. Let's see, I know it's a line, passes through 4. Slope is 2. And then, oh, kind of ran into my graph up there. Let's make this smaller. Let's make this, let's see, up to over 1 ohm here. This is going to be our hole. So it's a linear function with a hole at 3. So if it's not continuous, implies not differentiable. So because it has that hole, it's not differentiable. All right, here's going to be your challenge today. Writing equations of things you've forgotten from advanced algebra. Sketch and write an equation. And we should be able to stick with just lines and maybe parabolas. And I'll show you some. Refresh your memory. So here we go. I want a graph that is differentiable and continuous at the point 2, 3. So, if I think about something that's continuous and differentiable, I just need a smooth function, no cusp in it. So I know there's a line, a linear function, a parabola. So there's many, many, many correct answers here. So if I go over 2 and up 3, I'll do several equations here. I can go with a horizontal line. The equation for that line would be y equals, remember all horizontal lines are just y equals the number they're passing through. So that linear function derivative I know is 0 and it's continuous. Well, maybe I want to go with a line that's not horizontal. Maybe I'll go with one that passes through 1 and goes through that point. Okay, to write the equation of a line that's not horizontal, I just need the slope and the y-intercept. Well, I've got the b value equal to 1. It's crossing here at 1. The slope, if I count it, 1, 2, 1, 2, slope is 1. So I can go with the equation y equals mx plus b.